My name's Tom. I'm one of the senior software engineers from Flow. We're a Sydney-based software as a service platform company. I'll give you a little bit of an intro about what we do. My talk today is about how we kind of leverage ClickHouse to kind of accelerate and supercharge our billing pipeline stuff. So cool. Questions will be at the end. Cool. Alrighty. First, who we are and what we do. Who we are. Most of the dev team are here with me today. Good chunk of it. Not all of them. Shout out to those guys. Thank you for coming and supporting me. What we do. We sit kind of in the middle. Think of us as a kind of accelerator for your code. You provide us with your code hooked into GitHub. We automatically pull that off every time you make a commit, automatically package it up and build it, automatically deploy it, and then scale it and give you a whole bunch of other helpful features there. HA, we have managed databases with Neon. We have multi-region deployments. We have metrics, zero downtime deploys, logs, you name it, we have it. Cool, not too unusual. Cool, so we're pretty heavy users of K8s. Is everyone kind of familiar with Kubernetes? Anyone not? Show of hands? No? Okay, that's fine. Our infrastructure is split into kind of two main partitions. We have a services cluster, which holds all of our internal stuff, functionality, where we do our builds, where the app lives, the thing that allocates stuff out. Not going to talk about that one today. I'm going to talk about our other cluster, which is what we call our client clusters. These are the geographically distributed ones. These host to client workloads, and we have a cluster there per region for blast radiuses. Client isolation, good old K8s and namespaces plus Cilium. Cool. Alrighty, so what kind of data are we dealing with when we want to bill people? Our billing is consumption-based, which means the more you use, the more you get charged, and you only get charged for what you actually use. We primarily bill on CPU capacity, scaled out by the number of replicas you have, and your network egress. It's fairly straightforward. We have a variety of data, obviously, and anyone who's run a production Kubernetes cluster for hosting client workloads knows that you can get quite a lot of workloads onto a cluster. Those clusters can get big, and if you pack stuff in, you can get a lot of workloads onto a single machine. Cool. The pods we run, and the pods we harvest information from can crash or reboot at any time. They can be rescheduled. They can be redeployed by the user at any time. They can be scaled up or down, which means they're going to change in cardinality and shrink in cardinality. And certain identifiers can change on any one of these reboot conditions, which means you can't necessarily rely on stable identifiers, which means your pipeline has to handle a lot of that. Cool. The other critical thing for billing goes without saying, correctness. No one wants to be billed the incorrect amount. You don't want to overcharge people, degrades trust. You don't want to be oh, sorry, this one was actually supposed to be this. We're going to have to change your bill. Customers like predictable bills. Customers like bills they can understand. And customers like bills that are reliable, and the business often likes to change billing rules. So we want correctness, and we want permanency of data. If we came to a charge, we want to be able to keep that around in case someone goes, well, that doesn't make sense. I think, given that I only ran X number of services, you couldn't possibly have charged me this. So you want to keep everything around in case of that. Minimize runtime issues. No one wants a 2 a.m. wake-up call being hello, none of billing works. Please fix. That is the worst feeling. So we want minimize crashes. We want fault tolerance and resilience, and ideally a degree of self-healing. Cool. Also, because we're data engineers, we like lots of data. So the other thing that's important is latency. No one likes to wait ages for a bill. You don't want to use something and then 3 weeks in discover that someone's charged you some hideous amount of money for it. That is an unpleasant experience. You want to know what you're racking up as you're doing it so that you can adjust if necessary. Latency is important. Up-to-date builds are desirable, and data volumes can be large and frequent. Multiple metrics per pod, per timestamp, per cluster. Cool. Everything obvious so far? Cool. Right. That's good. Putting these all together, what does that leave us with? That leaves us with a system that is, we want immutable log structured storage, we are latency sensitive, and we are like read-write performance sensitive, because if we bottleneck up, then we're going to start accumulating data either at the edge or at the like write face, if you will. Neither of those are ideal. Reliable, ops friendly, that goes back to no one wants to be woken up at 2 a.m. Fault tolerant and resilient, because nothing is perfect, and ease of adjusting to business logic. I'm sure everyone's dealt with a scenario of PMs come to you and they're like, we have decided to change the deal. Pray we do not alter it further. And you're like, cool, okay. So we want something where a lot of this is kind of like locked away and doesn't affect everything below it. Cool. Alrighty, so to address the first one, ClickHouse's log structured merge tree tables are pretty much a perfect fit here. You write stuff in, off the hot write path stuff gets compacted into blocks. That's great. Columns oriented storage is again the ideal solution. Remember, we're going to be having lots of samples per metric, per pod, per cluster. We want to aggregate those up into totals, so we're going to need strong analytical features. Again, all-up database, exactly what we want. I've got 10K samples a second minimum here. I'm sure some of you operate at much bigger scales, but that was our like baseline of we need to be able to sync that. So which we do very easily, which is nice. Cool. We need to also be able to handle faults up and downstream, gracefully degrade without blowing up, and we want to minimize the number of moving parts. We don't want to splay this into 16 separate services, because then we have 16 points of failure and 15 points where the network exists. Hooray. Write should be idempotent, deduplicated, and safe to retry, and we want metrics and alerts on this, because the worst thing that happens is you get 4 hours into an 8-hour Spark job and it's like, tee-hee, I have broken. And you're like, great, that was the worst. I guess I'll just do it again. Cool. So these are all the things we want. So to address that, this is nice diagram of our data flow. We have client pods, C advisor, and cube state metrics. I'll get into those into a second. We have a placeholder here for what our billing pipeline is. ClickHouse there is our like storage and record. This little service, which I'll get to, and then Stripe, which is what we use for our charge platform, billing platform. Cool. Quick aside, anyone not who's used Prometheus metrics or okay, cool. Anyone? Okay, cool. This is Prometheus metrics. It's a text-based format. It's super duper common. It's a nice simple format for exporting useful metrics, usually counters and gauges out of applications. This is a sample of one of our new billing ingester actually. Applications will expose a /metrics endpoint. It's all text. You have something called prom agent, which like automatically discovers all the services in your cluster and then scrapes them and aggregates them up and then sends them off to you. That is because C advisor and cube state metrics are two sources of these metrics in a normal Kubernetes cluster. C advisor is from Google and it's called Container Advisor and provides quite literally an obscene number of metrics. It's actually like shocking how much there is. And it's like if you want to know what a container does, C advisor will tell you. It's like CPU usage, network, disk usage, like total bytes, it's everything. It's a shocking amount of data. Network egress, cool. And then cube state metrics gives you a whole bunch of like useful metadata, usually at the like pod deployment workload kind of level that C advisor doesn't get because C advisor is down at the like what's it called, your Docker runtime level. Cool. So that's our kind of like sources of data. That's what we need to do with it, and that's our requirements. This was our very V1 pipeline. It's pretty straightforward. You can see that billing pipeline part expanded into these two things, which is Prometheus Agent, which is a very slimmed down version of Prometheus, and Vector, which is a little open source tool for routing and processing logs and metrics and another number of other things. Very handy little tool. And then ClickHouse Billing Reporter and Stripe. So we'll just dive into these two real quick. Not particularly interesting. It scrapes things and then sends them off to you as a nice like protobuf format. Pretty easy to deal with. Vector is kind of like programmable data routing. You can set up little kind of blocks of things. It's all in TOML. Really low kind of like overhead, and we use that to get this stage of our billing pipeline, which is prom, vector, and then data flowing into ClickHouse, I think within about like under the first week of actually approaching this problem. So it's kind of like, we have no way to bill people, and then a week later it's like, we're collecting billing data, which I think is a pretty great turnaround for things. Cool. Onwards, we push batches into ClickHouse via Vector. We made extremely heavy use of the materialized views implementation and a couple of other things which I will talk about imminently. And then this is the one component that kind of does all our business logic, and it's in SQL. So it's nice and straightforward. It's not in programming language. I guess you could call it SQL programming language, but most of the logic around like backfilling, gap filling, observations carried forward, the boundaries of like billing start is all encoded in these like quite compact SQL queries, which means when we need to change those rules, we change them here and nowhere else, which is nice. Nice blast radius there. Cool. These are some of the like data samples of like what we get flowing in. It uses metric from cube-state metric or cube pod labels. Each of these tags is like just a plain key value pair of like everything that ooh, whoops, oh, there's a mic there. Everything that pod is tagged with, and then the timestamp, and then the value. A lot of these these cube-state metric ones, the value is not particularly interesting because we're more interested in this information, because this is what ties our containers back up to all our business logic, right? Because like customers don't come in and be like, I have a container of IDX. They're like, I've got a service. Oh wow. Okay, there we go. Can you guys hear me better, or was it better when I was just shouting at you?
Yeah, it's fine.
Yeah, cool. Alrighty. Right, so that's some of the data samples, and here's some of the stuff from C-Advisor. Once again, real. Should probably not stand in front of the speaker. Hey, real simple, pretty self-explanatory. You get an enormous amount of information in case you ever want to know what interface your customer's data is going out of. Cool. Hang on a moment. You may notice that I said we punch most of that into a single table. We do. It goes wholesale into this, so bearing in mind this is V1, into this metrics table. And we make great use of this visit param extract functionality that ClickHouse provides. It goes into there, and we pull information that we care about out into columns. This is obviously something that's pretty straightforward to do in a programming language, but when you want to minimize the amount of pieces in your pipeline and you want to like test it, make sure it's done, and kind of like basically minimize the number of moving pieces, having your database do it is fantastic. And you'll see the other half of why we do it in here in a second. But if you find yourself doing this, like getting dumped a bunch of JSON and being like, well, now I have to write something to splay it out into the columns. Some databases give you like explode I would say this leaves explode in the dirt because you can actually like parse the actual types out and control what happens when they fail there. I'll get into the codec stuff there because you can do some really clever stuff with that as well, which makes your life easy. And then the merge tree engine is obviously the log structured merge tree table type. The order by is important because that defines your physical layout on disk, which will define your read and write performance. Why use JSON? It's easy, ubiquitous, everything knows JSON, it's easy to debug, you can look at it and be like, that is missing all of the keys, that is wrong. Offloading this to the database is a massive developer win. I could just punch this stuff in and just be like, well, it's recording, and then now I can come back to this at my leisure. This is kind of like, I have this data and it is off the hot path, and now I can like address it at my leisure, which is fantastic. And being able to do it in SQL was nice as well. Minimizes moving parts, which is great. And now onto the other bit, which is materialized views. We're all data engineers. I'm sure everyone has like written a view or a materialized view at some point. Check out the ClickHouse ones. They're like materialized views that are supercharged. A lot of databases don't automatically update them, or they make you like manually refresh them, or something hideous like this. If you define a materialized view in ClickHouse, every time a block comes into your source table, the block is forwarded through the select of your materialized view automatically, and your table is incrementally updated, which is really, really, really nice when you're trying to join information in across different metrics. Because recall, some of my information came in on pod labels and some of it comes in on network bytes. I don't care what the container is, I care about these flow labels. And I want to attach container network traffic to these flow labels so that we can aggregate things properly. This also means no use for something like DBT or Spark or Matillion, which is really nice because that's one less moving part in your stack, which is great. Everyone likes less moving parts. And they automatically update. I think I already said that, but that's the winner. So it's not like you have to have it on a timer or something hideous like that. Cool. I'll whip through this a bit real quick. It's pretty simple. Went to great pains to make this as like reasonably idempotent as possible. You can run multiple copies of this thing. You can kill it at basically any point. Writes totals, not deltas, because writing deltas into Stripe came with too many risks of like, what if I write the delta and then I die and then I have to rerun? I have to make sure that you kind of two-phased commit to know where you are. That was pain. Writing totals in means that you can just like run it and then you can run it again, and if it's changed, well then it's updated. And if it hasn't changed, well then you've written the same thing in. Real nice. If anyone's familiar with CRDTs, this is similar to the convergence property. Hooray, CRDTs. This is also resilient to stalls upstream. If prom goes down, if vector goes down, if prom goes down, it'll just buffer on disk until vector comes back up. If vector goes down, similar things. This will just like sit and spin and just be like, oh hey, nothing's changed, that's fine. I just write it in and that's all good. When the data populates back in upstream, it reconverges on the correct result, and then Stripe just gets automatically updated, which is nice. I'm sure everyone's had those kind of like data pipeline fails where you're like, pipeline succeeded, and you're like, why is my data wrong? Wired into all of our prom alerts to be like, oh hey, your pipeline has stalled, which is really, really nice. Cool. In for the meme bit, written Rust uses like minuscule amounts of memory. If anyone hasn't written Rust, I recommend it. No exceptions and result types make writing software that doesn't blow up on you mid-pipeline like an absolute pleasure. You can put all the type hints into Python that you want. and it still doesn't come close to the surety you get from being like, nowhere in my code is a panic, which means basically if it compiles, it works, which is fantastic. Usage is done asynchronously per client, which means we don't have that kind of like big load anti-pattern where we have to like load up hundreds of gigs of data and then just like punch it all in downstream and hope that we don't fail midway. And if we fail midway, we have to start all over again. Do it async, don't compromise your throughput and minimize your memory usage. Cool. This is obviously the V1, which means there's a V2. So pros and cons. It was really fast to write. We had this up in a couple of weeks with basically one person working on it. But we started to incur excess compute usage, and we were using the database for more and more things. So we wanted to wind back some of that compute usage so that we could. I didn't finish my sentence there. Great, cool. We wanted to wind back that compute usage so we could get some query latency back on other things. Write latency was suffering. Back pressure was working, but not always how we wanted. Components, prom, and vector didn't give us all of the dials that we wanted. Often, if the write latency suffered too much, vector would stall, and then prom would stall, and then vector would recover, and prom would be like, no. Which is really annoying, so sometimes you have to go and kick the pod. Thoroughly unpleasant. Cool. Solution, rewrite it in Rust. Only sort of joking. I had to do it. Basically, what we did is we kept prom. We tore out vector for the billing ingester, which is the little service that we call it. Everything else remained basically the same, which was nice. So minimum disruption. If you're interested in the internals of it, we implemented the prom remote write protocol, which is just a protobuf over HTTP that goes into a ring buff, and then we asynchronously parse each of those metric types out into more compact types and write them async into the ClickHouse tables directly rather than using incremental views with a time of capacity buffer. So 10,000 rows or 30 seconds. Which is pretty nice. This thing hums along very, very nicely. Luke and I wrote this in 2 days flat, 1,500 lines, plus tests, plus dashboards. All of this is now under our control, which is great. Nothing much changed in terms of our overall architecture, but now we have the designs, the dials to change things as we want, which is handy. And our new table. Uses some new features as well. No more incremental views, no more massive JSON parsing. Strip that all out, add a little index, partition it, and use this handy replacing merge tree, which does deduplication of your order by keys when it performs the merges, which is really nice. We can talk about why, if someone's interested later, but picture's worth 1,000 words. So here's a performance comparison. Can you tell when we turned on the new one? It looks like it's 0. It's not. It's just so much more efficient that we basically don't even stress the database anymore. The workload's a lot more constant, which is really nice. CPUs like throughput, and this gives us that. This is a V1 pipeline. 12k rows, 220 meg, 217 seconds per write. We'd have 2 or 3 writes of these happening concurrently. Drum roll, that is the new one. 77 milliseconds per 10k rows, and 4 meg of memory usage. So that's why it's so much less stressed. Pretty fantastic. The reason for that, we swapped. Obviously, we got rid of writing JSON. JSON is fantastic and very nice and debuggy. Very nice to be able to debug. But plain text has a mighty big overhead if you're not keeping your eye into it. We designed the tables better. We were able to write directly to them, and we were able to batch things up in a way that was far more friendly to the internal architecture of ClickHouse. We were able to write entire page blocks in a row at once, rather than partial ones, and then it had to assemble them to write the block. We'd just be able to be here is 10,000 rows, and it'd be great, that is one page block. I'm just going to sync that right in. Smarter use of table engines, and just redesigning the tables to fit your queries. Our queries worked really well for our billing queries, and less well for everything else. The most queries I threw out, I've written billing queries here, but really it's most of them touch a single part on disk, which is a single segment on disk, which is nice. So we don't even have to trawl it, and that's within the partition as well. And everything basically has sub 100 millisecond latency. We spend more time waiting for it to go over the network and come back than the database actually does working on it, which is pretty fantastic. Row binary format. Shout out to this ClickHouse package in Rust. Packs things in a lot more efficiently because you get rid of all the JSON text overhead, more rows, less space, happier database. The only reason we can't do more rows in at once is because Prom doesn't have more data to give us, which I think's pretty great. And we have increased control over back pressure scenarios now as well. One thing we observed is that on certain back pressure, a common approach is block or drop newest. We preferred to drop oldest because if you have to drop something, you want to be recovering as soon as possible rather than lagging behind. So now, not that we need to, but if we want to, we have that control, which is nice. Cool. Here's some more nice graphs. This is the numbers on the side are correct. That is CPU as a percentage of limit. That is 0.3. I think we gave it, a tenth of a CPU, Luke? Yeah. So it 100 milli CPUs. For anyone familiar with managing workloads in Kubernetes. Memory usage is flat, constant. It's amazing. Put more workload under it, doesn't matter. Flat. No more we've got a ton of clients to build, and I'm getting an because I'm trying to load up all the data. Nope. Nice flat memory usage, which is great. And then this is the little histogram of batch sizes. So it's basically 50k row batch sizes. The line down here is dev at 10k. Less data in dev, obviously. Summary: if you need to save dev time, the materialized views are amazing. Compared to something like Postgres, and last time I used it, Snowflake. Having materialized views that will just automatically update, such a massive time win. Big use of that. Everyone likes the explain clause. Column codecs, I touched on very, very briefly, very big slept on feature. If you understand your data structure, and you understand your, the layout of your data, you can consume so much less space on disk without giving up query performance. Stuff like the double delta, that basically gives the database more information about what that type is. And double delta just means, if you're familiar with delta encoding, where you take first value and then you store only the diffs, double delta does that again for the diffs of the diffs. So for a block, you don't need to write the timestamp for every row in a block. You write it once and then just offset it, which is super useful. I think that is about everything. Do everything in database-friendly format. Make your databases happy. Make your life happy.
Applause.
Yes, questions?